Previously on Chemistry Z. Our heroes clashed with the ions in ionic compounds. However, by calculating the protons and electrons within each of them, they were able to pattern electronic configuration. But then, the ionic demon known as the Sixth Marker flew into the battle scene. If it wasn't for the ancient highlights, things would have been mad peak for our heroes. And now, with ionic compounds defeated, their eyes now set on covalent bonds. Will they be able to slay covalent the way they slayed ionic? Find out in today's exciting episode of Chemistry Z. Here are the retrieval questions for this lesson. You know what to do. It's electrostatic forces of attractions that hold oppositely charged ions together. Magnesium ions have a 2+ charge, and so they're in group 2, baby. To get ionic compounds to conduct electricity, you need to either melt or dissolve them. Now the ions are free to move around. See this top reaction. Now look at this bottom reaction. Pause the video and decide which one is covalent and which one's ionic. The top is ionic and the bottom one is covalent. Here is the difference between the two. Check the electrons. In ionic bonds, the electrons are not shared, they're taken away. It's almost like capitalist America. And so you see no overlapping shells, but you see these brackets that shows you you've got ions there. However, covalent bonds are communist. They share everything. So a quick summary, if they're sharing electrons, it's covalent. If they don't, it's ionic. We'll look at metallic bonds in the next video. We've been seeing dot and cross diagrams showing the outer shell electrons. You could also get displayed formulas showing the pairs of electrons as lines between the atoms. Notice that each line represents 2 electrons. You can also have ball and stick representations. The one here is a flat 2D model and the one you've got over here is the 3D model. The regular lines show the atoms that are laying on the same page as you're looking. The solid wedges is the atoms popping towards you out of the page, and the dashed wedges are the ones moving into the paper. So basically that atom is at the back of the paper. We have some limitations to using these 3 models here. That is that they do not show how the atoms are arranged in 3D spaces. And these 3 over here do not show the sharing of electrons, and all of them, they're not all the same size. We have 8 covalent dot and cross diagrams that you need to be able to draw, okay? Never forget. Hydrogen only has 1 electron, and so it needs another electron to complete its first shell. So a molecule of hydrogen shares a pair of electrons. Chlorine has 7 electrons, so it needs 1 more electron to complete its outer shell. So 2 chlorine atoms share one of their outer shell electrons, so they both now have 8 outer shell electrons. Oxygen has 6 electrons, so it needs 2 more electrons. That means that each oxygen shares 2 of its electrons, meaning that we have 4 electrons overlapping here. Remember that a single bond has 2 shared electrons. So Tatiana, what would you call this bond that's sharing 4 electrons?
A double bond?
Good work. Nitrogen is probably the trickiest. Each has 5 outer shell electrons, and so it needs 3 electrons each. Jaden, if the oxygen was a double bond, what do you think we'll call this one?
triple, innit?
We've got 4 more that you need to memorize, but what I'd like you to do is spend some time writing out the formulas of each of these molecules. Hydrogen is H subscript 2, chlorine is Cl2, oxygen is O2, and nitrogen is N2. Pretty straightforward. Hydrogen chloride, since both need 1 electron, they share 1 electron each. What you need to remember here is that the chlorine also has those 6 other electrons on its outer shell, so don't forget to include those. Water looks a little bit like Mickey Mouse. Since hydrogen only needs 1 and oxygen needs 2, the oxygen bonds with 2 hydrogen atoms, so each now has a full outer shell. 2 for each hydrogen and 8 for the oxygen. Ammonia has a nitrogen and 3 atoms of hydrogen. Nitrogen, being in group 5, needs 3 electrons, so it bonds with 3 hydrogens. Again, don't forget the extra electrons around the nitrogen. And finally, methane. Since carbon needs 4 electrons, it bonds with 4 hydrogen atoms, and all of them now have a complete shell. Looking at the chemical formulas, hydrogen chloride is HCl. You probably noticed that's the same formula as hydrochloric acid. That's because hydrogen chloride, when you dissolve it in water, it becomes hydrochloric acid. Water is H2O, ammonia is NH3, and methane is CH4. To help wrap your minds around all of that, look at this. Carbon monoxide is made out of carbon and oxygen.
Wool up, just wool up. What's a business, man?
Honestly, this is simple. Watch this. Carbon is in group 4, so 4 outer shell electrons, and oxygen is in group 6, so 6 outer shell electrons. That means that carbon needs 4 more electrons and oxygen needs 2 more electrons. This means that the oxygen gives 4 electrons to the carbon, and the carbon gives 2 electrons to the oxygen. But we shouldn't forget the rest of the electrons on the outer shell. Carbon has 2 more outer shell electrons, so we include that on the carbon. That's because it's in group 4, so it has 4 electrons in total. And oxygen has also 2 more electrons because it's in group 6, so we need to add 2 more electrons that are not within that covalent bond. The covalent molecules we've been looking at so far are called simple covalent molecules. Have a look at this table. What do you notice about these simple covalent molecules? Well, compared to ionic compounds, simple covalent molecules are usually gases or liquids at room temperature. And this is due to our good old friend, intermolecular forces. These are the weak forces of attractions between molecules. Look carefully at the image. We have covalent bonds that hold the atoms in the molecules together. These are strong. These do not break. I stress, these do not break. Intermolecular forces hold the molecules together, so the individual molecules are held together by these weak intermolecular forces. When we heat our substance, it's the weak intermolecular forces that break. Because these forces are weak, not a lot of energy is needed to break them. This is why simple covalent bonds have low melting and boiling points. Please don't say that it's the covalent bonds that break. These are very strong. It is the weak intermolecular forces that break. Remember, we looked at the heat curve of a substance in this video here. Click that to remind yourself on what that looks like. Here we have 2 molecules, A and B. I've got these 3 challenge questions for you. Pause and attempt the thing. We can see that the longer the molecule, the more intermolecular forces you have. This means that B would have a higher boiling point because there are more intermolecular forces that you need to break. if each intermolecular force needs 10 degrees of energy to break it, A would boil at 20 degrees Celsius and B will boil at 40 degrees Celsius. It's a lot more complicated than that, but we can run with that for now, okay? The last part of this lesson is all about polymers. Polymers are large molecules made up of many repeating units. Here I have two polymers, polyethylene and polypropene. Notice how the molecules that make each up are unique to that polymer. The smaller units are called monomers. These react together to form the polymers. Some common monomers have a double bond between carbon atoms. Each carbon has 4 bonds, and if the double bond is broken, each carbon can now join together with other monomers.
Baby, come closer.
The monomer in this example is ethene, and that makes the polymer called polyethylene. Clock how we write this, okay? Poly outside of the bracket, and inside the bracket we write the monomer. Scientists draw polymers like this. They draw the monomer with the broken double bond and draw brackets around it. There are 2 important things you need to make sure of. First, the brackets should cut through that broken bond, as you can see here, and also you need to write a small n on the outside to show that this is one of many repeating units. Here are some challenge questions for you to have a go at. The polymer will be polybutene. To get the 3 marks when drawing, you need to make sure that you have drawn the correct structure inside the bracket, then that the bracket cuts through the bond like I spoke about, and also you've got that small n on the outside. Alright then, it's time for you to know some real pain.
Just prepare to go to hell.
Nah, you're mocking it. It's almost the end of the lesson and you're backing out the 6th marker.
I don't have any time for any gossip now.
It really ain't that deep. Let's break this question down. Explain why chlorine is a gas at room temperature, but sodium chloride is a solid at room temperature. Include description of the bonding and structure of chlorine and sodium chloride in your answer. Spend some time answering this based on the last few lessons we have done. You could essentially write this out as 2 big paragraphs. Chlorine is a simple molecule with covalent bonds and weak intermolecular forces that need little energy to break. This gives it its low melting and boiling point. However, sodium chloride is a lattice structure with strong ionic bonds between oppositely charged ions that need a lot of energy to break, giving rise to the high melting and boiling point. And there we go! Lesson is done.
Fatality.
Make sure you collect the flashcards and the revision timetable from the description at the bottom, and I'll catch you guys in a bit.